I think we can start this session. The first speaker is Professor Jiro Soda. He will talk about the gravitational wave in the string versus.
Thank you. First of all, I'd like to thank the organizer for kind invitation. Today, I'd like to talk about the gravitational waves in the string axicals. You will see what is the axicals soon. Okay, this is from my talk. First, I will introduce the action dark matter, and then I'll explain. I'll introduce my recent work on this topic, how to probe this action dark matter with gravitational waves. Then, actually, we have come up with three methods. So today I will focus on one of them, that is using Chern-Simons gravity. Then, next, I'll explain how to explore the action dark matter with gravitational wave in this context. Then I'll summarize my talk. So, as you know, there are many evidences for the existence of dark matter. For example, CMB with a combination of with other observation, this CMB tells us that there is a dark energy, which is the majority of the energy density of the universe. And we also have the dark matter, which constitutes 25% of the total energy of the universe. So since the dark energy, since this is a very difficult problem, I won't mention about that anymore. Today, I would like to focus on this dark matter problem. So the question is, what is dark matter? Do you know that maybe the most people here believe that the dark matter is neutrino, or the so-called WIMPs. However, here I'll show the diagram. This project axis is the mass of the dark matter, and the vertical axis shows the dark matter neutron cross-section. Here we have the current limit by the xenon 100, and maybe now we have a more stringent constraint on the parameter space. And these are future experiments. As you can see, in spite of the many efforts, no evidence for dark matter has been reported. Moreover, no evidence of supersymmetry has been found at LHC. Since neutrino is a supersymmetric particle, this tells us that there is no reason to stick to the neutralinos. Therefore, it is worth investing in the other possibility. Here, we will consider the action as a dark matter. Since action is also part of the fundamental theory, this is worth investigating. So we consider both dominant and subdominant action dark matter with a wide mass range. Here we show another plot. Project axis shows the mass of the action. Here we have 10 to the minus 32 electron volt, and we have the 10 to the minus 20 power electron volt. And the particular axis is a fraction of the action dark matter among the total dark matter. This curve, this red region, brown region, is excluded from the observation of C and B. But as you can see, this is a 10% line. So that with any mass, we have some possibility to have, if we allow the subdominant one, then we can have the action with mass, for example, 10 to the minus 27 electron volt. So we have a lot of possibility. This is experiment from the experimental side, but even from the theoretical side, there are a lot of candidates for the action. Originally, action is invented to explain the strong CP problem, to resolve the CP problem, and in that case, mass is related to the decay constant with this formula. So, for example, if the decay constant is 10 to the 12 GeV, then mass should be 10 to the minus 5 electron volt. Moreover, there are other actions. If you believe string theory, in the context of string theory, there is at least a model independent action, which comes from the Karl-Lamont field. And there are a lot of model dependent action, which comes from Phong field, after the integration with respect to this cycle in this internal space. So the mass of the action is proportional to the e to the minus number of moduli. So depending on the shape, topological property of the internal space, this mass is determined. Because of this exponential dependence, we have mass distribution which is logarithmically flat. So we have the chance to have the broad range of mass for the action. Okay. So because from now on we'd like to probe the various actions with various mass. So the action for the action is very simple. This is action. This is Hilbert term, and this is kind of term for the action. And here we approximate the action potential by the quadratic potential. Usually it is quite good approximation. Then we can see the occupation number. Occupation number is easily calculated by this formula. Then here we assume that we borrow the number for the energy density of the dark matter, which should be 0.3 GeV per cubic centimeter. And here we assume the action mass 10 to the minus 10 electron volt. Then in that case, we have the 10 to the 38 for the occupation number. So it's huge. Since the occupation number is so high, we can describe the action field as a classical field. Classical field. And because the typical velocity of dark matter is 10 to the minus 3, you can see that we have the monochromatic frequency for the action. Then we can describe action by a coherently oscillating scalar field. Here, phi 0 is the amplitude of the oscillation. So action is oscillating with the frequency given by the mass of the action. Then we can calculate the energy density of the action. And As you can see, this is almost constant. So this amplitude of the oscillation is determined by the energy density of the dark matter and the action mass. So in a typical case, the amplitude is 10 to the 7 electron volt. And we can also calculate the pressure from this expression. Now that here we have different signs, so we have this result. Because of this oscillating behavior, if we average over the cosmological time scale, this vanishes. So on cosmological scale, we have zero pressure. That's why we can explain how this action can mimic the CDM for dark matter. But because of this property, we cannot distinguish the action from the cold dark matter on cosmological scale.
Before going, what is the precise definition of what is the precise definition of action, or is it just a very vague terminology?
Here we call action the pseudo scalar field. So in case of the in case of model independent action, this comes from the Karl Raimond field. So antisymmetric tensor field, which can be transformed into the pseudo scalar field. So point is that in case of pseudo scalar field, coupling is restricted because of the translation symmetry. So we can avoid the fixed force. So in my talk, we assume the scalar field is pseudo scalar to avoid the fixed force. Okay, so it's important to find some method to distinguish action field, action dark matter from the standard cold dark matter. In other words, we need to prove the existence of the action field with some method. So here the key point is the coherent oscillation. So as I explained, the difference appears as a coherent oscillation here. Of course, on cosmological scale, we can get the zero pressure after the averaging. But on a small scale, we have this oscillation. So combining this oscillation with gravitational wave, I'd like to I'd like to prove the action dark matter. So here, fortunately, in 2015, gravitational waves are discovered. Here, we have a clear chopped signal. And this year, these people got a Nobel Prize. And we have more events, at least 5. Now there are maybe 6 or 6.8, I'm not sure. And since we have 3 detectors, we can identify the direction of the source. And near future, Japanese detector Kagura will join this project. And LIGO India will also come into this network. So we are now in the gravitational wave astronomy era. So using this, so the point is that the gravitational wave will exist. So using this gravitational wave, we'd like to probe the action dark matter. So we have proposed 3 ways to probe this action dark matter. First one is done in collaboration with Aoki. Since the action is coherently oscillating, naively we may think this oscillation can be detected with gravitational wave interferometer. But actually this action oscillation is just standing wave, so we cannot detect this oscillation. But fortunately, we are moving in the halo, so because of this our motion in the halo, this action oscillation behave like a scalar gravitational wave. So using this fact, we propose that to use this gravitational wave interferometer to measure the action dark matter wind. This is one of the methods. And the other one is using the gravitational wave produced by the action dark matter. Because action is oscillating, this causes parametric amplification of the action itself. Inhomogeneity will be enhanced because of this action oscillation. Then this action makes the quadrupole component, then it produces the gravitational waves. And this can be, of course, this can be detected with gravitational wave detectors. And the final one is using the Chern-Simons gravity. Because action coupled to the gravitational wave through this Chern-Simons gravity, this coherent oscillation causes the parametric amplification of gravitational waves. So because of this parametric amplification, we have also the circular polarization of gravitational waves. So this can be detected, of course, using the gravitational wave interferometers. The important point is the mass range. These methods can probe. With this method, we can probe the mass, actual mass, with 10 to the minus 24 electron volt to 10 to the minus 18 electron volt. And with this method, we can probe the mass from 10 to the minus 24 electron volt to 10 to the minus 4 electron volt. And this method, this is the topic of today, can probe mass range 10 to the minus 14 electron volt to 10 to the minus 10 electron volt. The point is that this is complementary, but this includes both. So we have at least 2 ways to probe the action with the same mass. Okay, let me explain what is Chern-Simons gravity. So the Chern-Simons gravity is just given by this action. The difference is distant. So this is a topological term. If phi is constant, then this is just a number. This does not affect the instant. But because action coupled to this topological term, this becomes non-trivial, and this produces parametric resonance. And here we have parameterization of the coupling constant. L is length scale. From now we call this coupling constant. This Chern-Simons term naturally appears in string theory. And from the point of the effective field theory, adding this term is natural. This is just the momentum expansion of the action. And indeed, this action has been investigated as a modified cell gravity for a long time. And actually, they already exist a post-Newtonian constant on the coupling constant from the gravity probe B experiment. And probably in future, the gravitational wave give rise to some constant on this coupling constant. Here, the result of the gravity probe B, because the Chern-Simons term affect the frame dragging. So from this experiment, the result of the frame dragging effect is consistent with general relativity within this accuracy. So this gives rise to this constant on the coupling constant. So coupling constant L should be less than 10 to the 8 kilometer. This result is obtained recently. So now this is the constant on the coupling constant. But in future, using the binary system which emits gravitational waves, which waveform can be easily calculated using the post-Newtonian horizon. The result is here. The point is the phase. We can measure this phase. This phase consists of two terms. This term comes from general relativity, and this delta psi is the contribution from the Chern-Simons term. This contribution proportional to delta C is here. So the Chern-Simons term affects the spin-orbit interaction, the spin-spin interaction. So here we have the coupling constant. So this represents the Kerr parameter, the spin of the black hole. I should say that this is a black hole binary system. So if we can measure the Kerr parameter, spin of the black hole, then we can constrain the coupling constant. Then these people conclude that in future we can constrain this coupling constant to be L less than 10 or 100 kilometers. This is the current situation. So now I'd like to consider another method to probe the by which we can probe the action dark matter. And it also gives a new constant on the coupling constant of the Chern-Simons gravity. So we focus on this mass range 10 to the minus 14, from 10 to the minus 14 to 10 to the minus 10, because it corresponds to the frequency range 1 Hz to 10 kilohertz. In this region, the advanced LIGO can probe. Okay. So from now on, just we concentrate on this mass range. So you note this picture. As I said, the action is coherently oscillating. Since action is dark matter, action exists everywhere in the universe. And if there exists a binary system, this emits the gravitational waves. So the gravitational waves are propagated in a strange axis. Okay. So since I like to discuss the circular polarization, it's convenient to introduce the circular polarization basis. So this is standard gravitational polarization of standard gravitational waves. If you consider that gravitational waves propagating to z direction, the polarization is described by this metric. So this is a plus mode, so just the oscillating this way. And the cross mode is just a rotation of this mode by the 45 degrees. So using this basis, we can calculate the quadratic action for the gravitational wave. Starting from here, we can linearize the metric, then we obtain the quadratic action for the gravitational wave. Here we neglected the cosmic expansion because in the halo we can completely neglect the cosmic expansion. Then we get this result. The point is here, epsilon A is the sign factor. Epsilon is 1 for the right-handed polarization mode. Here we have sign difference for the right and left mode. So we get this sign difference. So that means that the equation motion is different for right and the left. Okay. And we have here the oscillation. From this action, we can obtain this equation motion. Then you can see that because of this cosine term, we have the parametric resonance. Resonance frequency is given by this formula. For the 10 to the minus 10 electron volt, we have 10 kilohertz. And we have solved this equation motion numerically, then obtain this behavior for the right mode. You see that this is 10, so the amplitude is enhanced by 10 to the 10, but for the left hand, this is 8. So the amplification is 10 to the 8. So there is a difference. So because of this difference, we have the parity variation in gravity sector. The red line, red part is, this is the frequency, and this is time. So as the amplitude the growth, this parity variation is also growth. So we have completely circular polarized gravitational wave here. So if this parity variation pattern is observed, this should be evidence of the action dark matter. This is my first conclusion. And let's here we assume the gravity probe B result is we report that the gravity probe B gives rise to this constraint. And we support the action is the main component of dark matter. Then from the standard calculation for the parametric resonance, we can calculate the growth rate analytically. Then we get this result. This growth rate can be translated into the time scale for which the amplitude will get enhanced 10 times. Then after the propagation, here this formula tells us that after the propagation of 10 to the minus 8 parsec, we get 10 times amplitude. So since the size of the galaxy is about 10 kiloparsec, so after the propagation of 10 kiloparsec, this gravitational wave will be, the amplitude will be enhanced by 10 to the 10 to the 12. This is absurd. So actually, we have never observed this phenomenon. That means we should have at least this number for this time scale. So we obtained a new stringent constraint to L must be less than 1 kilocent. So we have improved 8 orders of magnitude. That's the second result. Then finally, if we assume the coupling constant is observed by the gravitational wave interferometer, then suppose the L is determined to this value, 100 kilometer. Then in that case, after the distance scale becomes this. So in the universe, action dark matter is coherently oscillating even in the void region because of the action field consists of dark matter. Because of that, we took this value for this is average density of the universe. Then mass, we assume mass 10 to minus 10 electron volt, and we assume the coupling is 100 kilometer. Then from this growth rate, we can conclude that action dark matter can be observed by gravitational wave interferometer up to omega equal 0.01, 1%. So even if the action dark matter is not dominant one, we can probe this action dark matter up to this fraction. So at the same time, of course, we should observe the parity violation in the gravity sector. So let me summarize my talk. We have the proposed three ways. Today, I explained one of them. This chance-simon term gives rise to the useful tool for probing the action dark matter. That's it. Thank you.
We have time for a few questions or comments.
Is there any reason why you consider this particular vibrational coupling instead of like Gauss bonnet or other coupling?
Thank you. I didn't talk about the Gauss bonnet. In principle, we can do the same thing even for the Gauss bonnet. Because why I didn't talk about the Gauss bonnet is comes from the fact action is pseudo-scalar. So the action naturally coupled to the Ponderian topological invariant. But since Gauss bonnet has a parity invariance, so if we couple action to the Gauss bonnet, so it produces the explicit breaking of the parity. That's why I didn't.
Do we have constraints from observation on that coupling, on that parity violating coupling, from other observation?
I don't think so. The only constant available now is from the gravity property.
Any other questions? I have a naive one. So naively, I would say the coherent oscillation is very unstable. So you have very small perturbation and you will dump its energy to gravitational wave. So is this coherent oscillation stable?
So we are considering the action dark matter whose coherence length is in this case, for this mass scale, the coherence length scale is 10 to the minus 3 parsec. So here we have this time scale. So we have enough time for the action, the amplitude action growth. And this coherence is very stable because the evolution of the action, if you take into account the coupling to the gravity sector, this is nothing but the parametric amplification. So there is the self-tuning of the phase. So this coherence is stable under interaction.
Okay, if there's no further question, let's thank the speaker.